Oh,
Our new SCP podcast. Our first episode discusses the origins of the Foundation.
well, I'm having trouble here. Ah, okay, maybe we start over again, huh? Click on Zoom. It says my account. It says meetings. And what I want is thermodynamics from 11 to, well, it says 1. Okay. It says join. Open Zoom meeting. Start video. William Vang, hey. Looks like you're on board here, William.
Hey,
Good. Wonder if I got anybody else. I wonder if there's anybody else. Oh yeah, we got Alex, Andres, Brian, and some other wonderful students here. Nathan, Mohammed, Julian, Daniel, and Nicholas. Hope I didn't leave anybody out. Okay, well, welcome back. We're in thermodynamics now. We've got a good class. And it's going to start. Oh, it's 11 o'clock. It's time to get started here. What have we been doing? Compressibility, that's what we've been doing. Ideal gas law, PV diagrams.
good morning, Professor.
Say that again, please.
Hey, Professor, this is Reagan. I have a question.
Yes, Reagan.
I was having a trouble to post my homework on Blackboard, so I
Yes.
email you. I email you the homework. I don't know if you see that.
Well, let me look here, Reagan. It looks to me like you've got all of your homework except except number 6, and
It's
I
number
don't know if it's not due yet, is it?
It's already due.
Well, let me look and see if it's due. Hey, just a minute.
Okay.
Homework number 6. Let's see. It's due. Yeah, I think it is due. And you had trouble posting it, Reagan?
Yes, I email you the homework. Yeah.
That's okay. I'll get it, and that'll
right.
be fine. It'll be okay.
Thank you.
Yeah, thank you. Anybody else have a comment or question? Okay. Well, what are we going to do today is the question. Let's start with one of these compressibility things, shall we? Here we go. We're going to do a compressibility thing. All right. Let's suppose you're dealing with methane. And suppose the reduced pressure is 0.7, and the reduced temperature is 1.1. Now, if you go to the back, you can find the critical temperature of methane. It's in the back, and you can find the critical pressure of methane, and you can find the critical temperature of methane. Let's just pause for 60 seconds and go to your tables there. Can you get to your table somehow and get those critical, you know what those are? That's the top of the vapor dome. Go ahead and get those for me. Look them up in the back of your book. I know you can do this. Methane. And then tell me what they are. And I'll go to my friend, well, I was going to go to Nathan. Nathan, those are on table A.2. See if you can find them, Nathan. What is the critical pressure for methane? Earth calling Nathan.
Yeah, I'm here. Okay. Critical pressure for methane. CH4. There it is. See, that's 4.6.
Good going. He knows how to find it. And as long as you're on that page, Nathan, what's the critical temperature? That's the top of the vapor dome. What's that temperature?
190.4 Kelvin.
Good going. Okay, we got that. Now we're going to pause for 60 seconds or so, and I want you guys to find, Z for me. They call it the compressibility factor. Now remember, to find that, you've got to go to a graph, and that graph is on, it's figure D.1. Find figure D.1, plug in these critical pressures and temperatures, and I'm going to do it, and see if you can find the compressibility. I'm going to try to do it. Here goes. I'm doing it now. Well, I think I know what the Z is. Let me go to my friend. Let's see. We'll go to Braxton. Braxton, I never pick on you. Did you look at that graph and get the compressibility, Braxton?
Yeah, I got 0.8.
That's what I got. It's exactly what I got. Okay, now we're going to find the specific volume. Here we go. We're going to go PV equals ZRT. Now we know what R is. Well, no, we don't. But we can find it. But you know, we don't know P and T. These are the critical pressures and temperatures. The way it works is PR is equal to your pressure over your critical pressure. Well, look, we know the critical pressure. Yeah, we know that. We figured it out. We looked it up. And we know the reduced pressure. Yeah, we know that. That's given. So you can find the pressure. And the same with the temperature. The way it works is the reduced temperature is equal to the temperature over the critical temperature. And we got that. One of my excellent students helped us with that, and we know that that's given. See, that's so you can find. Look, you can find the temperature. You can find the pressure. And we got the Z figured out. I bet we can find that R too. Here, let me look that R up. I'm going to look it up. Some of you might want to look it up. Well, what are we dealing with? Methane. Okay. Let me shop around here and see if I can find methane. Gas constant, methane. Here it goes. 0.5183. It's 0.5183.
In which table did you get that R value from?
Thank you for asking. At table A.5, look on A.5 and get the gas constant for methane and see. Now I got everything, and I can find the specific volume. Okay. Well, let me write all this stuff out. I need some room here. Where am I going to put it? Not much room there. I need these values of P and T. Let me do that. PR is 0.7 times 4.6. Let me write it over here. P is 3.22 megapascal. Now let me get the temperature. 1.1 times 190.4. T is 209.44 Kelvin. So we have everything. We just need a little room to write this stuff. Let me write it out here. I need some room here. PV, only this has got to be in kilopascals. You don't use megapascals. 5183. And then the temperature is 209. Okay, we got everything we need. Go ahead. I'll shut up for almost a minute and find for me the specific volume. Go for it. Well, let me ask some of you guys. How about my friend Andres? Andres, unmute. Tell me what you got for the specific volume.
I got 0.02697.
That's what I got. Good going, Andres. Okay, well, we did a problem. We did a methane problem. Now, I'm just curious, do we have a methane table? Let's look and see. I forget whether there's a methane table back here, but I'm going to go back here and I'm going to look. Well, there's water. I'm looking for methane back here. Yeah, there's some methane. Let's try to look this up in the methane table for fun. Don't you think that'd be fun? Here we go. We know the pressure, 3.22 megapascals. 3.22 megapascals. Well, and the temperature, we know that's 209 something. See, you know what the problem is trying to look this up in the tables? We would have to double interpolate. They don't have a 3.22 megapascal table. They have a 2,000 and a 4,000. We're closer to the 2,000, but no, wait a minute. No, we're kind of halfway between, aren't we? We're kind of halfway between. But what about the temperature? 209. Well, oh gee. You'd have to interpolate. We could spend another half hour using double interpolation to find this. But I don't want to. That takes way too much time.
Mr. Griffin,
Yes, go ahead.
I am getting the specific volume of 0.0374, not 0.0269.
Okay, well, let me put these numbers in my calculator. Here goes. I'm going to take, thank you for speaking up. I'm going to go 0.8 times 0.5183 times 209.44. And then I'm going to divide by 3220. And what I get is 0.0269. 02697. Do yours again. You're pushing the wrong button somehow, Mohammed. I
Got
think,
it. Thank you.
yeah, I think you just,
Thank you.
we
I was
all
putting
do
the
it.
wrong temperature. Thank you.
Yeah, we're okay. Well, I don't want to waste your valuable time doing that long double interpolation. That would be ugly. But we could, it's possible we could get the value from the table. All right, well, let's do a different one. Unless somebody out there is just dying to do a double interpolation, I'd like to move on. Because they're nasty. All right, let's find one here that I want to do now. Let's see.
Hi, Professor.
Yes, I'm listening.
Can we please do, let me pull out the problem quick here. Can we please do problem on chapter 2, 1110E?
Yeah, I'll be glad to. Now it's chapter 2, and it's problem 1, what now?
110E?
110E.
Yes.
And tell me your name, please.
That's Reagan.
Oh, yeah, Reagan. Okay, Reagan. That'd be fun. We'll do that.
Thank you.
Yeah. I just got lost a minute there, and I found what I wanted to do here. Okay, now I'm going to find for my friend Reagan, and it won't hurt the rest of us, not at all. And let me find this now. 110E, okay. I'm looking for it here. Hey, I found it. 110E. Okay, we're going to do ammonia now. Let me write this down. That's ammonia at 100 Fahrenheit. @80 psi. Okay. We're going to do it 3 different ways, Reagan. The first way is the best way, and that's the tables. So you go back here and you find ammonia in the tables. And I'm looking for ammonia. Looking for ammonia in the tables. Hey, I found it. Now, I've told you guys you're supposed to go to the vapor dome table first to sort of locate where you are. And I've told you the secret to success is the PV diagram. I keep telling you that over and over again, hoping that you'll listen to me. Now we're going to locate where 100 Fahrenheit is. Well, it's kind of towards the top of the table, but it's not at the top. The top is at 132. But 100 Fahrenheit, wait a minute, I'm on the wrong table, just a minute. I'm on metric. This is Inglés, senor. We got to find ammonia in Inglés. I was on the wrong table. Okay, now I've got ammonia. Yeah, there it is. And I've got the vapor dome table. They call it the saturated ammonia table. And what we want is 100 Fahrenheit. And you know what? It's right in the middle. It's right in the middle. Well, if it's right in the middle on the table, then it's right in the middle on your PV graph. Now they said we got 80 psi. Well, we have to find out what this saturated pressure is at 100 Fahrenheit. Well, what is it? It's 211.949. This is 211.949. I need a couple of you to look that up for me and tell me that's correct.
That's
Can
correct.
anybody? Yay, good, excellent. But see, we got 80 psi. Well, 80 is way down here someplace. It's 80 is smaller than 211. So if you come over here, ooh, there you are. There's state one. It's at 80, see it? Okay, now that's superheated vapor, folks. So let's go to the superheated vapor table now. Shop around and find 80 psi. There it is. And then we want 100 Fahrenheit. Oh, there you go. I found it. It says the specific volume at state 1 is 4.1861. Wonder if I did that right. Yeah, that's right. You'll find that at table F.8.2. Look on table F.8.2 and you'll find that. Now go back to your problem and let's see what we're supposed to do here. I got lost there. I need the problem. Gee, what problem are we doing?
It's 2110
Thank you.
10E.
Yeah,
There you go.
I got lost, but I'm back. I'm okay now, and I've got to find it here again. I got lost. Okay, there it is. We just did it. We just found the answer. Now this is the best answer. I'll put a happy face on that. That's the best answer. Now we're going to do it with the ideal gas law. Okay, let's do that. In other words, we're going to go PV equals RT. And we're going to solve it using the ideal gas law. Well, the pressure is 80 psi. Here, let's write that like this. That's pound force per square inch. You're going to have to multiply by 144 square inches per square foot.
Mr. Griffin,
Yeah, go ahead.
you put the wrong units on the specific volume of 4.1861.
You're absolutely right. I'm so proud of you. It's cubic feet per pound mass. Good going. Was that my friend Mohammed?
Yes, Mohammed.
That's yours, Mohammed. You helped the class because that was wrong. That was wrong. Appreciate your help. Okay, now we're going to look up this gas constant for ammonia. Yeah, so let's go in the back. And we want the English gas constant now. So I'm looking up the English gas constant for ammonia. and it is 90.72. Foot-pound force, pound mass, Rankine. Now we need our temperature in Rankine. And it's roughly 560 Rankine. Being a little bit lazy, it's really, you're really supposed to take 100 and add 459.67, I think is what it is. But that turns out to be about 560. Let's just call it 560. Okay, now do I have everything?
Hey, Mr. Griffin,
Yes.
I can take it from there now.
Say that again, please.
I can take it from there. I got
Oh,
it.
you don't need me anymore.
No, you don't need to finish the whole problem.
You don't need me anymore. He doesn't need me anymore. Now,
I've got a question. This is Nathan. I've got a question.
sure.
So the R value is what was holding me up, and you said it's 90.72.
Yeah.
Okay, and I just want to be sure where you found that's the English units. Where is that?
Let me show you where I found it. Thank you for asking. I found that. It's got to be in the English place. It's table F.4. F.4. You'll see it there for ammonia. 90.72. So see if you can find it.
I did find it. Yeah, I found it. I'm just trying to figure out how to go to the right table here. I see that it's in the right units, but it says properties of various ideal gases at 77 Fahrenheit, 1 atm. I don't know. I have a hard time going to the right table to get these R values for some reason.
Yeah, now do not be fooled by that 77. That's room temperature, and 1 atmosphere. That's our sea level pressure. They've measured these things at that. It's what they call standard atmospheric temperature and pressure. But that gas constant is a gas constant no matter what the temperature and pressure is. Just because they measured it at standard values, all those numbers are good. You don't have to have atmospheric pressure in order to use these values in this table. They shouldn't have put that in there. It's just the temperature at which they performed the experiments. I don't know if that explains anything, but
I think it does. Thank you.
yeah, do not throw all those out and say, well, it's not atmospheric pressure, so none of these are any good. Well, that's not the case. And then you're going to get an answer that's going to be off. And Reagan knows that, and he can do that. And then the third way you do this problem is with the compressibility. But if you're all happy, I'm going to move on. Reagan says he doesn't need me anymore, and that's up to the rest of the class. We're going to move on, and let's move on. I want to do one similar to this, but on this one I'd like to go through all three methods. Now this is again ammonia, but this one's going to be in metric. You guys like metric better, I know. So unless there's somebody that needs me, I'm going to erase this. Okay, we're going to erase that right there. Goodbye. English ammonia problem. And we're going to do an ammonia problem in metric. It's going to be at 140 Celsius. Come on now. There we go. 140 degrees Celsius, 10,000 kilopascal. And we want to use the tables. First of all, we're going to use the tables. And then we're going to use the ideal gas law. And then we're going to use compressibility. That's the plan. Okay, well, here goes. You know you're supposed to draw a PV diagram. And go back there, this time to the metric system stuff, and find ammonia. Okay, I'm looking for ammonia. In the metric, not the English this time. We need 140 Celsius. You know what? 140 Celsius is above the vapor dome. The top of the vapor dome is 132 Celsius. 140, it's a little higher up than the vapor dome. It's kind of like that. 140. It never, that isotherm never enters the vapor dome. Now let's look at the pressure. The top of the vapor dome is 11,000 something. That's 10,000. Well, it's in here, 11,000, or no, 10,000. 10,000 kilopascals is in here. So there's our state one right there. Now, in order to do that, I had to look at table B.2. Do you have any questions so far on how I did that? Well, if you're happy, okay. We're going to find the value of specific volume from the tables, but it's going to be in the superheated vapor table. Go to the superheated vapor table. Look up 10,000. Hey, I found it. Look up 140. Oh, that was easy. Well, what did you get when you go to table B.2.2 is actually what you want here. B.2.2. Somebody tell me what they got.
0.01195.
That's what I got. Now that's the very best answer that you're going to have because it's from the tables and that's the best model. Now we're going to do the ideal gas law. Okay. Well, we know where we're at. I'm going to erase that because I need the room here to do the ideal gas law. But we know where we're at. We're out there in the superheated vapor region. And we're going to go PV. We're going to go PV. Here's your P. And there's your V equals. Now we need that R. Okay, help me shop around and find the gas constant for ammonia. I'm looking for it. Gas constant for ammonia. 0.4882. Okay, well, we got R. PV equals RT. What's the T? It's got to be in Kelvin, folks. All right, we're going to add that up. And I think it's 4. I did that in my head. That's kind of dangerous. Did I do that right? I think so. Okay, let's get the volume that way. Here goes. I'll shut up a minute. I'm getting kind of hot, so I'm gonna open this door a little bit, let a little cooler air in here. Go ahead and get that. I guess it's going to be another hot day. The last hot day, because it's supposed to get colder this week. Well, go ahead and get that V and we'll check you here in a minute. Okay, I got a value of V here. I got 0.0201, you could round it off, I guess, to a 7 cubic meters per kilogram. Now, that's pretty good. Look, this is the correct value from the tables. That's pretty dang close, isn't it? It's not bad. So that's the ideal gas oil. It came out pretty good. In fact, let me get the percent difference here. Oh my, that's very accurate. So ammonia at this particular temperature and pressure pretty much is behaving like an ideal gas. Okay, well let's find ammonia or the specific volume using the compressibility. Now that'll be fun. All right, let's do that. We've got 2 of our values. Now this is with the tables. Let me make a little, I'll put it up here in the corner. Using the tables, we got 0.01195. Using the ideal gas, we got 0.02017. Okay. Well, let me make a little room here and then we'll do it with this compressibility business. Here we go. See, we've done this problem with the tables. We've done it with the ideal gas. Now we're going to do it with compressibility. Here we go. Okay. Well, don't we need this PR and TR thing? Let's look those up. The PR is going to be, it's going to be 413. Oh no, it's going to be, well, it'll be 10 megapascals. divided by, and you're going to have to snoop around and try to find that for ammonia. And I'm looking now. Okay, I'm trying to find it. Here we go, ammonia. It's 11.35. Now let's get the reduced temperature. Reduced temperature. Well, we need the, it's got to be in Kelvin. And you divide by, oh gee, I lost my place. I just had it. We need the temperature. I lost it. Here we go. Temperature ammonia. 405.5. Now, does anybody need help finding those numbers? Just speak up. I guess you're okay. All right, let's get these amounts. Here we go. 10 divided by 11.35. That's 0.88. It doesn't have any dimensions because it's just a ratio. Now this one, 413.15 divided by 405.5. I get 1 point, rounded off, 102. Now we have to go to that graph and read that stinking graph. Okay, well, we can do it. You know that graph I'm talking about. It's this crazy graph here on page figure D1. We need to go to figure D1. All right, and I'm going to look up 0.88. Okay, let me see if I can find that. Well, I see a 0.1, and I see 1. Well, 0.88, won't that be between 0.1 and 1? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8. That's dang close to 0.9. It's just a shy to the left of that 1 there. And then you go up to 102. Well, do they have a 102? Not exactly. They have a 1.0 and a 105. I bet I could probably get pretty close to that. So let me go up here. And we need 102, right? Right. Well, it's a little bit subtle. It kind of looks like Z's about 0.6. It looks to me, reading that graph, that Z is about 0.6. Now, if you got 0.61 or 0.59 or even another digit off for those, do not change your major. It's pretty close to 0.6. Now we're going to do the third method. Here goes. PV equals Z RT. Well, what's the R? That's the 0.4882 kilojoules per kilogram Kelvin. And the temperature is 413 Kelvin. Okay. And the pressure is, well, it's 10,000. You got to put in 10,000 in here. kilopascals. Okay, now we're going to solve that. We're going to get the specific volume that way. All right. All right, I'm doing that now. Well, I'm getting you know what? Staring at this, I think I told you the wrong thing. I think I went 0.0195. There's two ones there, isn't there? I'm going to have to go back and revisit that. But here's what I'm getting for the compressibility value. I'm getting 0.0121 cubic meters per kilogram. Now that's much closer to this than that is. I mean, 12 is closer to 11 than 20. Here, let's get the percent errors on these. Did that make any sense to anybody? I hope it did.
Yes.
Great. I'm going to get the percent error on this. I did that wrong here a minute ago. And what I'm going to do is I'm going to subtract these and divide by that. Here goes. Oh, gee. There's a tremendous error here. There's a 68% error between those two. Now I'm going to get the percent error for this one. Using the ideal gas law, I got a 68% error. That's bad. You know that? Now, using the ideal gas law, I mean the compressibility, you'll take this, you subtract the correct value, put a happy face on it. There you go. And then divide by the correct value. So here we go, 0.0121. And then you divide by, or subtract 0.01195, divide by 0.01195. And this gives you a 1.2% error. That's 1.2% error. Gee, that's a lot better than 68% error, isn't it? So it's an improvement. It's definitely an improvement over the ideal gas law. Did you have any questions on that? Well, let's practice some more here. Practice is good. Anybody have a comment or question on that?
Professor, this is Nathan. I'm still a little bit confused about the figure D1, where what do the vertical lines represent? I see the PR and I see the TR, but what are the vertical lines for?
They're to help you with the reduced pressures. And it's Nathan I'm talking to, right, Nathan?
Yes.
Yeah. Okay, well, here, let me try to draw it. You don't need all this. You're taking excellent notes. I know you guys. You've got the you've got this PR thing down here, reduce pressure. And in here you have a 0.1, and here you have a 1. Now what we want, I erased it, but we wanted a 0.88. Well, see, 0.88 is about here. Now they have a dashed line, Nathan, that does this, and you know what that is? That's the 0.9 reduced pressure line. They've got a dashed line there. It's just barely this side of the 1. Because see, there's 1, there's 0.1, there's 0.2, there's 0.3, there's 0.4. They get smaller, 0.5. It's logarithmic, it's not linear. And when you get to 0.9, you're pretty dang close to 1. No, that 0.9 is where I did my dashed line. There you go. And you go up this dashed line. Now we got to find the reduced temperature. It's 102. See, this was the reduced pressure. Well, they don't have a 102. They do have a 1.0. And it's a little bit subtle how it goes. But it goes like this. It comes down here, and then it goes like that. So 1.0. And on this side of it, they have a 105. And it goes like that. That's the 105. See, well, what we want is a 102. Well, it's going to be kind of in here, closer to the 1. And in between the 1 and the 105, they're pretty close together. We're right here, bullseye. We're right there, Nathan. And then you go over here. And what I got, when I did.
Professor, I think
Yeah.
I see what I'm confused about now.
Yeah.
Those vertical lines with the 0.8, 0.85, 0.9, 0.95, those seem to be corresponding to the Z factor.
Those are the temperature lines. You're talking about the 0.8, 0.85, 0.9, Nathan?
Yeah, I'm confused about those.
Okay, well, let me show you those. These are all bigger than 1. There's a 1, there's a 1, this is a 105, and then there's a 1.1, and somewhere up here there's a 1.3. But you see, there's also numbers reduced temperatures less than 1. There's a 0.8. Now the 0.8 does this. It comes down here. And then it goes straight up. It's really weird. It goes straight up, 0.8, and then it cuts over like that. That's the 0.8. And then they have a 0.7 and a 0.6. The 0.7 comes down here, goes way the heck over here to 0.7. It goes straight up, and then it cuts over here to the right. Those numbers are dealing with the reduced temperature lines. Did that help any?
I think so. So for now, kind of ignore those markers and just look at the.
If your reduced temperature is bigger than 1, you want to ignore the reduced temperatures that are less than 1. Absolutely. But if you have reduced temperatures less than 1, you don't want to ignore them. You got to live with them.
All right, thank you.
Yeah, thank you for asking. Okay, well, that was good. And those questions, I'm sure, help people. Anybody else, comment or question? Here's your chance. Well, what about homework? Let's see what the homework is. This is the 8th, right? Yeah. And on the 8th, I think I just did the homework for you. Your homework is 110E, and one of my excellent students wanted me to do that, but I didn't finish it, did I? I just helped them a little bit. Which is, so you finish that and you turn it in, and it's due Friday night at midnight, I think. But it's good. Turn it in. That's your homework. And I helped you with it a lot. That's good. Excellent. And there's your test is available Thursday, and you have 3 days to do it in, and it's due the 13th. Your test is this weekend. Did you know that? When's the 13th? I got a calendar here.
Monday.
It's the Sunday. Sunday night at midnight. Make sure before then you get your test turned in. And of course, it's open book. You can use, that'll help, won't it? I mean, you're at home. We're doing online stuff. So I'm sure you can do that. Well, let's practice a few more things here, unless you have another comment or question. And I don't mind doing homework for you. I don't mind it. I just want you to understand this stuff. So when you
Are
go
we going to have a class on Thursday, Mr. Griffin?
this Thursday?
Yeah, or we just have the
Oh,
test?
absolutely. Yeah, we're going to have a class this Thursday. Yeah. Yeah, we don't want to miss class. We love coming to class, don't we? We like class, don't we, Mohammed?
Yeah.
Yeah, sure. Okay. We're just using the CO2 table now. So we're going to go to CO2, carbon dioxide. Yeah, you know that. I think when you breathe, don't you breathe in oxygen and breathe out carbon dioxide? Okay, now I want you to see if you can find, I want to see if you can find, if the pressure, I want you to find the specific volume. When the pressure is 2,000 kilopascals and the temperature is 118 degrees Celsius. I'm going to shut up and let you work for 2 minutes. There is a CO2 table. So see if you can find the CO2 table and see if you can find that specific volume. Go for it. I bet you can. You don't need 2 minutes, but go ahead and see what you can do. Well, I think I have the answer. But we better check it. I'm getting 0.03549. I wonder if that's what you got.
That's what I got.
Yay, good. I bet it's right. Did anybody need help with that?
Yes.
You need help with that? Well, here, let me write it out for you. We need to go to the CO2 table, and we're going to have to interpolate. We can do that. We're going to take 0.0335.
I'm looking at table B32. That's
Yeah.
not the right table?
Yeah, that's the right table. Table B.3.2.
Oh, my bad. That I was looking at 20,000 kilopascals, not 2,000.
Oh,
That's
no,
my problem. Sorry.
Yeah, that's your problem. Do I need to continue, or are you guys okay?
I'm okay.
Okay, all right. Well, I think that's the right answer. We did great. Now we could try doing that with the ideal gas law. Let's do that just for fun. PV equals RT. Here it goes. We're going to use the ideal gas law now. I'll shut up and let you do it. Well, why should I have all the fun? Go ahead. I'll be quiet. Do it with the ideal gas law and find out what it is with the ideal gas law. Go. Well, I got what I think it is with the ideal gas law. Anybody out there get that?
Yes, I got the same.
Yeah, excellent. Well, this is the best answer. Do you understand? Here, we'll put a little happy face on that. Let me see what the error is, just out of curiosity. Well, it's not bad. This is only off by 4%. You're probably not able to read these pressure and temperature gauges much better than 2 or 3%. So this is pretty good. It sort of behaved like an ideal gas. Well, let's do another one. That was fun. Make a little room here. Anybody have a comment on that? Are you okay? All right, well, here goes. I'm going to erase that now. All right, bye-bye on that one. But we'll do another carbon dioxide. A lot of this is just review here. This time I want you to find the pressure. And we're going to give you the temperature. And I'm going to give you the specific volume. Can you read all that? Yeah, you can read it. Okay, again, I'm going to shut up for a couple of minutes. We need to find the pressure. We have the temperature and the specific volume. We're going to find the pressure. Okay. I wonder if anybody's got that. How about my friend Alex? Alex, do you have that yet?
I'm still working on it.
That's fine. Take your time. It's a little different. We're trying to find the pressure. What about my friend? How about Julian? How about my friend Julian? Do you have that yet, Julian?
No, I'm still working on it. Sorry.
Yeah, that's fine. It takes a while. Well, here, let me help you here. If you go back to the tables, B.3.2 is what we want. It takes a while to locate this, but we're between 2,000 kilopascals and 3,000 kilopascals. And at 100 Celsius, at 2,000, this value is 0.03359. And at 3,000, this is 0.02182. What we want is 0.02960. Now it's between 29 is between 21 and 33. And so what we want is a pressure between 2,000 and 3,000. Maybe that'll help somebody. I'll be quiet for another minute. See if somebody can get that. Hey, William, how you doing on that? Earth calling William. Come in, William. Well, he must have gone out for a minute. See, what you got to do is you got to find this difference and the big difference. Here, let me write it for you. Now, after you find that ratio, then you multiply by this big difference, which is 1,000, and you add it. You add it to the 2,000 because the numbers are getting bigger. Going from 2,000 to 3,000 is getting bigger. And if you put that in there, here's what I got. I got 2339 kilopascals. Check me out. Make sure I did that right. Let me make sure I didn't goof up. I think that's right, guys. That's how you do it. Now, just for fun, let's do it with the ideal gas law. We have 4 minutes left in class. I think we can do it. Let's see, there's a little room up here at the top. Let's use that. Got a little room here at the top. PV equals RT, all right? Only this time we're trying to find P. And we know V, 0.0296. It's point, oh geez, is it 1882? Is that what it is? I can't remember. I'm gonna have to look it up again.
889.
Say again, please.
It's 0.1889.
Oh, thank you so very much. It's 0.1889. And now you gotta watch out for the temperature. It'd be 373. Hey, we can solve that. All right, here goes. I'm solving it. Let's see what the ideal gas law would say. Well, I got an answer. I got the pressure using the ideal gas law would be 2381. And let's see how close we came. Well, that's not terribly bad. See, this is the best answer. Do you understand? This is using the tables. We'll put a happy face on that. Let's get the percent error just out of curiosity. Here goes. Oh gosh, I got it's only 1% error. 1.5% error. If I did that right. That's pretty good. So it's, Go ahead.
I'm getting a 1.76. Is that still okay?
1.76 for the percent error.
Yeah, is that still okay?
Let me write that. The way you would write that would be, see, this is the correct answer.
Mm-hmm.
You'd write 2339 minus 2381, which is what you get with the ideal gas. You divide by 2339 and multiply by 100. Now let me do it again. I might have got that wrong. 2339 minus 2381 divided by 2339. You're right. You're right. Give you a thank you point. It's really more like 1.79%, isn't it? Is that what you said?
Yes, yes.
Yeah, it is. It's 1. Somehow I pushed the wrong button. Still pretty darn good. Less than 2% error. Well, we've had fun, and you have some homework to do. I guess it's due Sunday. No, that's not right. When is your homework due? Let me look and see here. Oh, we're running out of time. Oh no. We're running out of time. It says here, this is the 8th. Oh yeah, that's that one. That's that one that I helped. I think it was Reagan. Yeah, 2-110E, and it's due on the 11th, which is the 11th is Friday night at midnight. You got some homework to do for me. But our time is up. We've had a good time. I hope you enjoyed it. And I'm going to sign off unless you had a last comment.
Thank you.
Thank you.
Thank you. See you on Thursday at 11.
Bye.
Bye-bye.